Well, hello everybody. Welcome to Physics Colloquium. It's my pleasure to introduce Peter Love from Tufts. So Peter was an undergraduate and PhD student at Oxford before, I can get this all straight now, postdocs at Queen Mary of London, Tufts, and for several years was employed at D-Wave Systems before going back to academia. He joined the Haverford College faculty in 2006, and that's where I first met Peter. So my senior year at Haverford was his first year, where he taught me quantum mechanics. And I see a couple of my former students in this room, so I'll tell a quick story about Peter's quantum mechanics course.
Oh, no.
You know how I got to be the way I am. So I think it was the first upper division undergraduate course you taught at Haverford. And there were 3 exams, 2 midterms and a final. The first midterm, I went and dug up in my office. I think had about an average of 98. We just owned it. So for the second midterm, I think the average was somewhere in the 70s. There's a little bit of overcompensation.
Yeah, this train's going to go well.
But the final was a thing of beauty. I want to say it was 4 hours, closed notes, closed book, 5 questions, stepping through building a qubit piece by piece. And so I see those of you who've had my exams can see what I'm aspiring to. So wanted to let you know where I got that hope from. It was a fun exam. My peers would say that, but I enjoyed it. But Peter left Haverford for Tufts in 2015, and he's been there ever since. And it's my great pleasure to welcome him here and quantum simulation.
Thank you. So is this working? Can everyone hear me? So it's a great pleasure to be here. It's great to see Jonathan in his new role and to be at a department with the good sense to hire 2 of my former faculty comrades, both Jonathan and Stefan. The other story about that exam is one of the exam scripts, I won't say whose, had an annotation on it that said, I finished this exam and came out and realized that Kurt Vonnegut had just died. And that's, this is not going to be a good day. Okay, so let me tell you a little bit about quantum computing, which is a field that is really exploding with interest and excitement and some hype in the last few years. So the whole field got a huge boost in 1994 when Peter Shor realized that you could factor large numbers using a quantum computer efficiently. So it's easy to tell that 15 is 5 times 3, but if I ask you for the factors of this number, which in all the years I've used this slide I have never actually worked out, you will have a much, much harder time. This is an esoteric problem, but this problem is, the hardness of this problem is the basis of RSA security, which still encrypts a large amount of your internet commerce. The response to this, actually I was on a panel last week with a guy from GCHQ, which is the British NSA. They steal your secrets, but they're much more polite about it. And he said that GCHQ has been spending a lot of time not on solving this problem on what's called post-quantum cryptography, which is classical cryptography, runs on regular computers, but is based on mathematical problems that are likely not amenable to quantum attack. Lovegrover, slightly later, realized you could search databases in a time the square root of the size of the database. If it takes linear time, classically, you can do it in the square root. Less impressive than this, but still very interesting. But a little earlier, no other person than Richard Feynman suggested that you could simulate quantum systems with a quantum computer that's simulating. I hope I don't have to persuade people in this room that understanding quantum mechanics is difficult. On a classical computer, it's difficult. But on a quantum computer, it appears to be much easier, and that's what I'm going to tell you about today. I should make a comment here that finding new quantum algorithms is extremely hard. I think I've spent a long time with little result trying to find the next Shor's algorithm. It's a highly romantic quest to go on, but it takes a long time. You shouldn't think that these are things you're going to trip over in your pajamas. I should point out, actually this is slightly out of date, but this Simulating Physics with Computers is now Richard Feynman's most highly cited paper. It's well above his work in high-energy physics, for example, which I don't exactly know why I'm telling you that, but it's a curiosity. So let's think a little bit about classical simulation, and there's a distinction that's useful to bear in mind in what I'm going to talk about. So analog simulation, here's what's called an orrery, rather like a clockwork model of the solar system. This is the Wright brothers' wind tunnel, and this is a MIT wind tunnel, presumably somewhat more advanced. Here, the mantra is the same equations, the same physics. So the motion of the clockwork planets will allow you to predict eclipses and occultations and things like that. The Reynolds number here, even though the model aeroplane is smaller, will be the same as in the real Navier-Stokes flow over the actual aircraft. And actually the Wright brothers did a lot of wind tunnel work before they flew, and the same is true here. The alternative to this, of course, is digital simulation, where all the simulation variables are discrete. This is a millennium simulation of structure formation in the universe, slightly more advanced than this model. And these are two computational fluid dynamics simulations of, I think this is an F-16, already obsolete. So the difference between these two approaches is if we discover an extra planet, actually it's been going the other way, if we lose a planet, you have to delete a whole piece of this apparatus. If you want to do a simulation that's twice as big, you only have to add 1 bit to your position variables of all the things in this simulation. The same thing is happening in the quantum simulation domain. Analog simulations, for example, this is atoms trapped in an optical lattice in an experiment in the lab, and it's trying to understand the physics of this cuprate material. This again, my slide needs updating. Digital simulation, however, you construct quantum bits, which I'm going to talk about more in a minute, so that the variables here are all discrete. Everything is described by an integer, and yet we're able to do the first simulation here of this helium hydride ion, and you can see, I realize this data is rather noisy, but you can see a clear dissociation curve here. And I'll show you some slightly better simulations later. And again, if you want to simulate a system that's twice as big here, you need twice as many atoms. Here you need to add 1 more bit. Okay, so I said quantum bit, so I should explain what it is. This is my favorite quantum bit. This is a postcard that Walter Gerlach sent to Bohr in 1922, and this is the actual silver atom mark from a Stern-Gerlach experiment, which, if you remember, the silver atoms go through the magnetic field gradient. Here there's no gradient. Here the gradient is on, and I get exactly 2, or the beam splits into exactly 2 things. This is a spin half particle, because remember, a silver atom has only 1 electron floating around outside a bunch of closed shells, so they're like little cheap neutral electrons to play with. And so here we have an example of a 2-state quantum system. Okay? And any 2-state quantum system can be used as a qubit. We can describe the state by 2 amplitudes, an amplitude for 0 and an amplitude for 1. And Born's rule, of course, tells us the probability of being in 0 and the probability of being in 1. The time evolution of our qubit, if we imagine a silver atom going through a inhomogeneous magnetic field, it will evolve in some way. But according to the Schrödinger equation, there'll be a little Hamiltonian, which will be a 2x2 Hermitian matrix. One of the mildly confusing things about quantum information is we don't usually think about Hamiltonians. What we do is we cook up some real physical Hamiltonian, we evolve under that Hamiltonian for a fixed amount of time, and we look at the unitary operator. So the formal solution of the Schrödinger equation is, of course, we exponentiate IHT over h bar, and then we just regard this little unitary matrix that maps the state of the qubit at time 0 to the state of the qubit at time t, and this we call a quantum gate. It's just a discrete action on the qubit. That way we can tell our experimental colleagues, please do this gate however you want, and then we can cook up how many gates we need them to act on. So it creates a nice division of labor. We can count how many gates we need to accomplish a particular task. We can tell our experimental colleague how many gates we want. They get very cross with us and say, no, we can't do that many gates. And then we try and reduce the number of gates and so on and so forth. So what are the experiments made of? Well, there are three leading approaches to quantum computing right now. The first is quantum optics. This is the quantum optics setup. It's extremely difficult, I apologize, it's extremely difficult to show you a quantum computer. If you look at pictures of quantum computers on the internet, usually you see a picture of a dilution refrigerator, which is like me offering you a beer and showing you my fridge. Okay. So this is a quantum optical setup, which there's not much to see, but there's a photonic chip inside here. Trapped ions are more fun because the trapped ion qubit is two of the hyperfine states, the same two states that are used in an atomic clock. If I shine a laser beam on one of them, when the qubit is in state, I always have to check my own slide here, 0, the atom fluoresces. The laser drives a transition with that state. And so a bright dot here is a fluorescing ion. That's a state 0. The dark one has a laser shining on it, but the one state is detuned from a transition, so it's dark. So the dark state there is not a missing atom, it's just one. And then this is a superconducting circuit realization. This is a Google, you have to count the qubits, 1, 2, 3, 4. So this is an 8-qubit chip from a few years ago. But the point is that you can abstract away from the hardware. Just think a qubit is any two-level system. What's the state of the art right now? All the applications are chasing the production of systems with about 50 qubits in them. With about 50 qubits in them. I always have to say that twice because when I started working in this field, there were 0 qubits. And they have about 1% errors, which you should think of as representing the number of sequential operations you can do on the qubits before the output turns into garbage. So you should think, I can do a few tens of repeated operations on these chips before I get absolute rubbish coming out. Okay, let me tell you a little bit about gates and what to do with them. Here's a 1-qubit gate. This is called the Hadamard gate, after Jacques Hadamard. What does it do? It just takes a 0 state and makes it into the uniform superposition of 0 and 1, takes the 1 state and makes it into the uniform superposition with a sign 0 minus 1. That's a 1-qubit gate. What about 2 qubits? Well, here's an example of a 2-qubit gate. This is actually a classical gate in the sense that it doesn't generate any superpositions. What does it do? Well, here are the states of 2 qubits. There are 4 of them. I can have my 2 qubits in 0, 0, 0, 1, 1, 0, 1, 1. There's an amplitude for each of those possibilities. What does this gate do? It sends 1, 0 to 1, 1 and 1, 1 to 1, 0. In other words, if this high qubit up here, it's called the high qubit because it's on top, is 0, nothing happens to this low qubit. If the high qubit is 1, its value is added modulo 2 to this qubit. In other words, it does a NOT gate on the low qubit. So this upper qubit is controlling the lower qubit. Now, let me tell you a fact. If I have these gates, these 2-qubit gates, and I have arbitrary 1-qubit gates, then I can make, out of a sequence of those gates, any transformation on qubits. So really, I only need to ask my experimental colleagues to do 2 things. Make me a CNOT and make me an arbitrary single qubit rotation. And then we can do anything with some sequence of those gates. So all this, if I assemble everything together, I get the quantum circuit model, which is just a way of writing down time evolution in quantum mechanics. So I have a single qubit. I can denote some action on the qubit by a little box labeled by U. Time runs from left to right. I can write complex circuits, so many lines and many gates. So here's a little circuit. I start with this qubit in state 1. I start with this qubit in state 1. I do the Hadamard. I do a controlled knot. And hey presto, what comes out here is the singlet state. And I can denote a register just by drawing a little line here with n qubits. So how should you think about this stuff? Well, it's exactly like sheet music. So the qubits run from left to right. The gates are the notes in the symphony, and you just follow along and follow along and follow along. Can anyone recognize what tune this is? Sorry? Sorry? It's Ode to Joy, I think, actually. It used to be God Save the Queen, but then I got annoyed about Brexit and made it Ode to Joy. Okay, so let me tell you about how to, using these gates, how to accomplish a task that we should all be very interested in, which is determining energy eigenvalues. So the first thing we're going to do is prepare an energy eigenstate. So our state psi here is going to be some eigenstate of a Hamiltonian that generates a unitary operator. So when I act with the unitary operator u, it evolves by a phase, e to the I omega t, where omega is the energy divided by h bar. So how am I going to measure this eigenvalue omega? So let me just give you a little sketch. I'm going to have an ancilla qubit that I'm going to start off in state 0. And I'm going to have an n qubit energy eigenstate that I have prepared by hook or by crook. What happens next? I apply a Hadamard gate to my ancilla. So now my ancilla is in a uniform superposition of 0 and 1. I'm then going to do a controlled evolution. So if this upper qubit is 0, I do nothing. If the upper qubit is 1, I evolve the lower qubit by my unitary operator u. What does that do? That gives me two branches to my wave function, one in which the eigenstate has not evolved, and the other in which the eigenstate has evolved, so it's developed a phase e to the I omega t. But you'll notice that psi multiplies both of these wave functions, so I can separate out the phase e to the I omega t as now being a relative phase on this ancilla qubit. So here, of course, this is a global phase, if that's all that's happening. But now, because this is a controlled evolution, this phase that I'm interested in has become a relative phase on my ancilla qubit. So I've encoded into the state of my ancilla qubit what the number that I'm interested in is. And so now all I need to do is figure out how to extract this omega, and I'm going to tell you a really slightly dim-witted but easy to explain way of doing it. So I just do another Hadamard gate on my ancilla, and now, rather than being relative phase, this gives me an oscillation of the amplitudes. So this is, again, not the most efficient way of doing this, but if I just do a bunch of experiments and let that state evolve for varying amounts of time before measuring 0 and 1, the probabilities of 0 and 1 will oscillate exactly with the frequency that I'm interested in. So, and then we could determine a frequency by Fourier transforming this classical data that I've obtained by many, many repeated experiments. So this, what I've told you, is just a formalization of Fourier transform spectroscopy to determine the eigenvalues, with the exception that u of t could be any model Hamiltonian we're interested in. That is put in by us in a way which I'm going to spend almost the rest of the talk explaining how to do. Now, what do we need? We need to write a circuit for this thing. Now, if you're sharp, you'll be saying, Peter, you clot, why don't you just take a Fourier transform of this thing and determine the frequency directly? And of course, that is what you do in the real version of this algorithm. So what I've described to you here is something called phase estimation. It's a way of reading out eigenvalues as in the full phase estimation algorithm, you can read out a sequence of bits from the quantum computer that are the digits of the energy eigenvalue. And that phase estimation algorithm really underpins Shor's algorithm, and it underpins most of quantum simulation, and it's sort of the workhorse quantum algorithm. Okay, but we still need to know, how do we simulate time evolution on a quantum computer, on a system of qubits? So now we're doing quantum simulation, so we really want to start with a physical model, which means I want to ask you to write me down a Hamiltonian, but we can't just do anything. We need to specify some notion of what's an easy Hamiltonian. How do we specify a Hamiltonian in a way that that isn't itself exponentially hard? After all, an arbitrary Hamiltonian on qubits is a 2 to the n by 2 to the n matrix. If I ask you to tell it to me by writing down numbers on a piece of paper, this is not an efficient specification of the problem, so I can't help you, because you're specifying the problem inefficiently. So there are two natural ways of expressing a Hamiltonian. The first one is just to use locality. It's a very natural idea in physics that we would use locality. Here we don't really mean geometric locality. We just mean how are the qubits coupled together by the Hamiltonian? Are they coupled in pairs, even though the pairs might be rather distant from each other? Or are they coupled in triplets or quadruplets? And so we quite happily think about Hamiltonians that are made up of terms like this, as long as we have a number of terms that doesn't grow too fast with the number of qubits. We can write down all the terms, and we have a Hamiltonian we can specify easily. The other natural idea of a simple Hamiltonian is a sparse Hamiltonian. So this is a one-sparse Hamiltonian. A one-sparse Hamiltonian is, as a matrix, has only one non-zero entry in each row in each column. Now, of course, a diagonal Hamiltonian has that property. So a one-sparse Hamiltonian is just take a diagonal Hamiltonian and then get very confused about where your rows and columns are, okay? So you just scramble up your rows and columns, and that's a one-sparse Hamiltonian. So again, if I can express my Hamiltonian as a sum of a reasonable number of one-sparse terms, then I've got an efficient specification of it, because I can tell you just a function that tells you where the non-zero entries are, what their values are, and I've specified the Hamiltonian. And just a bit of language that you won't know because we made it up. This approach to simulation is based on what are called direct mappings, and this is on compact mappings. Don't worry, I'm just going to use those words, so that's what they mean. Okay, so now we have to simulate this operator. It's the exponentiation of a sum of these terms, which are efficiently provided to us. And so now we undergo a process called Trotterization, which is named after someone called Trotter. It has nothing to do with pigs. So what do? We just discretize time. So we take time slices. And then within each time slice, we approximate this exponentiation of a sum by a product of exponents. So we have to have little n here be quite large for this to be true, because it is not in general true, of course, that e to the a plus b is not equal to e to the a times e to the b unless a and b commute with each other. Okay? So every time we do this approximation, we incur a little bit of error, because we're ignoring the non-commutation of the terms. The other problem with Trotterization, apart from analyzing the errors, which can indeed be a bit of a pig, is that the cost scales polynomially in inverse error. So what that means is if I want to reduce the error by a factor of 2, I should expect to have to increase the length of my circuit by a power of 2. So that's not very good. So these approaches are the simplest way of doing quantum simulation, but they also lead to very depressingly long circuits. Nevertheless, let me tell you how to do the actual simulation. So suppose I take a particular term like this. Trotterization says all I need to do is learn how to evolve under one term, or each term of the Hamiltonian. So this is my example. So what do? Well, first of all, x, z, y, and x, this is too much mess. So I do a gate that rotates, y to z, x to z, y to z. So I rotate all these things to the z direction, and then I evolve under z, 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 and then I undo my rotation. So all this says is that any term like this is locally equivalent to some evolution under a big product of z's. And how do I do a big product of z's? Well, this is the moment where I realize I didn't define the tensor product. So if I take z tensor z, this is 1 times minus 1. So this is a diagonal matrix, 1 minus 1 minus 1, 1. Okay, so that's what I mean by the tensor product in matrix form. So what does this do? Well, if the first qubit here is 0, the first z just multiplies by 1. If the second qubit is 0, multiplies by 1. The third qubit is 1, multiplies by minus 1. So this z, 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 it counts the number of 1s in the bit string it acts on. If that number of 1s is odd, this z, 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 z term multiplies by minus 1. If it's even, it multiplies by plus 1. And so all I have to do here is count up the 1s. So I can do that I can count how many 1s there are by adding this one to this one, then adding that one to that one, then adding that one to that one. And then I can rotate around z just on this qubit, because now this qubit is 0 if the number of 1s is even, and 1 if the number of 1s is odd. And then I undo my calculation. So with all that, I can simulate this with a number of C-naughts which is just linear in the number of qubits coupled. Okay, so in the compact mapping, this is even more complicated. So I'm just going to tell you that it's a fact that you can evolve using a quantum circuit under a diagonal matrix. And if you take a one-sparse matrix, that's just like a diagonal matrix with the entries moved around. So as long as you can compute where the non-zero entries are, you can, and what their values are, you can also evolve under a one-sparse matrix efficiently. So in both of these cases, the Hamiltonian is composed of a sum of terms that act locally on the qubits and a sum of terms that act, or a sum of terms that are each sparse. You can efficiently simulate time evolution under those Hamiltonians. Okay, I just want to mention briefly that only a few years ago now, we managed to get rid of this nasty problem with Trotterization, and now there are exponentially more efficient ways in terms of error of simulating these time evolutions. Okay, all of that is rather complicated and much too complicated to run on the quantum computers we have today, which, remember, have about 1% errors, and so you can only do a few hundred gates on them. So these are called NISQ, or noisy intermediate scale quantum devices. So here are 3 experiments done on NISQ devices, one with photons, one with superconductors, and one with ions. And what do? Well, instead of doing all this time evolution, what we want to do is find the smallest eigenvalue of a Hamiltonian H, like this. And so what we can do is construct on the quantum computer an ansatz state for the ground state, and then estimate the expectation value of each of these terms in that ansatz state. And then we can variationally minimize the state by repeatedly measuring the terms, repeatedly estimating the energy, and changing the parameters of the ansatz state. So therefore, instead of doing these very long coherent evolutions, that we need for phase estimation, we can do many, many, many short evolutions for this variational method. And in fact, on this plot, which was done on the Google machine, the red lines are this variational method, and the little crosses here are this phase estimation method I was just telling you about. So you can see the machine does not have enough coherence to accurately do the phase estimation method in these regions, but this variational method just cruises through because it needs much shorter evolutions. And if you go to Google's website or to IBM, you can download Python code that implements this variational method, and they have tutorials, and so this is something you can just learn about in your own spare time. So those three examples were both chemistry, and so I wanted to talk a little bit about why is chemistry a good problem on a quantum computer. This is a picture of S.F. Boys in 1950, and this is the EDSAC vacuum tube machine in Cambridge. I always like to joke that this is S.F. Boys, but everybody in England looked like this in 1950. And so this is a plot from our paper back in 2005 showing the number of spatial basis functions used to represent a molecule and the number of qubits one would require. At the time, this was very important to us because up around this number of qubits, you start being able to break RSA cryptography, which means you will not be allowed to keep that quantum computer. So the idea that these problems, some of these problems represent, say, the cholesterol molecule at a level of accuracy that will never be accomplished by any classical machine. So these represent difficult problems that nonetheless chemists would be interested in solving that would only require a few hundred qubits. So how do we do this? Well, chemists are experts in discretizing problems in a basis of what are called molecular orbitals. An orbital to a chemist is just the eigenstate of some single particle, single electron problem. So it could be an atomic orbital like you learn about in your introductory to quantum mechanics classes, or it could be what's called a Hartree-Fock orbital, where the average effect of all the other electron-electron interactions is included. But you should think of it pictorially as a function rather like these, spherical harmonics. And we use, when we simulate this on a quantum computer, we use the second quantized representation. So we just have an operator that populates this orbital or depopulates it. And in that form, we have a second quantized Hamiltonian, which has two terms. This is the single electron term, and this is the term representing the electron-electron interactions, which is where all the interesting things happen in chemistry. So now, using this language of direct mappings and compact mappings, we can use a little bit of 1928 technology. This is the Jordan-Wigner paper showing how to map spins to fermions and fermions to spins. Now, if I use a qubit to store the occupancy of an orbital, that means the qubit is telling me, is there an electron in this orbital? And is there an electron in this orbital? But then you have a problem, which is I can't just use this operator, which obviously changes a 0 to a 1, or this operator, which changes a 1 to a 0, as my raising and lowering operators, because those operators will commute with each other. And if I have two fermionic creation and annihilation operators, they will not commute with each other. Okay, if I exchange two electrons, the wave function has to change sign. What that means is that the operators have to know about all the electrons that are in between them and another occupied orbital. And so what we do is we allow our qubit operators to grow a big long tail of z's. And so I'm a qubit creation annihilation operator. I have this horrible tail trailing behind me that could go from me to the last qubit in the register. But then when you multiply me by another such operator, the tails overlap with each other in exactly the right way that these give the correct anti-commutation relations. So this representation, this direct representation, just maps the occupancy of these orbitals to a bit string in the quantum computer. And the wonderful thing about that is that you can write down problems with, say, 50 or 100 orbitals that are very, very difficult for chemists to solve on regular computers today. If you go and look at the exascale chemistry project at Brookhaven National Lab, the problems that those guys are interested in are really up at the sort of few hundred qubits level if you use this mapping. It's also true, though, again, you should be saying, there's a silly thing here. You know, the number of electrons is a good quantum number in chemistry. If you look at the periodic table, the number of electrons changes. That means you're looking at a different atom. So the direct mapping I just told you includes everything from all zeros to all ones. So it includes all the sectors of what you call the Fock space. So the compact mapping is introduced so that we restrict, we only look at the parts of the problem that have 2 electrons in, or 3 electrons, whatever we're interested in. And then the advantage is that the chemical Hamiltonian in this basis is sparse. So we can either use a direct mapping, where we have the occupancy is mapped to a tensor factor, or we have this compact mapping where the Hamiltonian matrix is sparse. And in both cases, we can simulate the time evolution. You know, I've frequently been to talks where I've thought, you know, this speaker really included too much stuff. I think this is maybe not the first time I've done it, but this is the first time I'm realizing it as I'm speaking. But I wanted to get to this stuff because I'm very excited about it. So I apologize if this has been too brief. So quantum chemistry has now really become well established. There are many groups working on it. The group at Google is working very hard on it, and IBM are working very hard on it. So, you know, if you're an academic, at that moment, it's time to start thinking about something else. So it's always been a puzzle to me why do chemistry problems look so different from quantum field theory when you put things on a computer? So there are some very obvious things to say. In chemistry, you have a trivial vacuum. It's just all the lowest energy orbitals are occupied and everything else is vacant, and then you have excitations above that. You have basis representations that require 10 to hundreds of logical qubits. In quantum field theory, the vacuum is a very active and difficult part of the theory. You have renormalization, so you cannot just put in a bare parameter and expect your results to come out correctly. Typically, in quantum field theory, you know, you think about representing a classical field on a computer, you immediately throw a grid in. And so most approaches to classical field theory on a computer use a lattice. There are some nice papers by John Preskill and collaborators on simulating quantum field theory, and they are, in the technical language of our discipline, very daunting, the gate replies, which means that I don't want to tell you in case you go running out of the room. So, fortunately, the connection between chemistry and field theory has been thought about by Ken Wilson, because Ken Wilson's father was E. Bright Wilson, who was a quantum chemist. And so in 1990, Wilson wrote this nice little paper about ab initio quantum chemistry. Ken Wilson is the creator of lattice gauge theory, among many other things. And he says that ab initio quantum chemistry is an emerging computational area 50 years ahead of lattice gauge theory. So in this paper, he has a suggestion, which is to use something called the light front formulation of field theory. The light front formulation has the following nice properties. It has a trivial vacuum. It has an orbital basis formulation, so you can think about it like chemistry. And so the natural question is this good for quantum computing? So here's the paper that really the light front was introduced in. Actually, it was introduced periodically throughout the 20th century after this, so by a group of extremely distinguished people. So Lenny Susskind and Steven Weinberg all have papers on basically the same idea. So what Dirac says here is that if you want a fundamental theory, I want to upset my chemistry friends, but chemistry is not a fundamental theory. You need two things. You need a relativistic invariance, and at the time of writing, you needed a Hamiltonian formulation so you could quantize it. This is the same year as Feynman's paper on the path integral, I think. So relativistic invariance just implies that you can have different coordinate systems in your theory that are related by Lorentz transformation. But it implies something that's not immediately, or was never apparent to me until reading about this stuff. What Lorentz invariance means is that if you have a coordinate system, you can construct all coordinate systems that are equivalent to that under all Lorentz transformations. But starting with any given coordinate system, you don't get every possible coordinate system that way. In fact, you have to have 3 kinds to get everything. So the one that we always think about is the instant form, where I define my dynamical variables on a space-like surface. Okay? So a surface of constant time. There's something else called the front form, where I take all my dynamical variables to live on a light front, a plane wave light front propagating at the speed of light. And then there's something even more bonkers called the point form, which I'm not going to talk about. So of course, most QFT is constructed in the instant form. This talk, or the remainder of this talk, is constructed in the front form. And it's a property of human groups that every human group wants to have within it some member who is regarded as being the outsider. So to instant form, the front form is the outsider, and to the front form, the point form is the outsider. So it's nice that they're organized like that. So we can look down on it. But in all seriousness, there is a little bit of work formulating field theory in this, and it's just worse. It seems just more complicated. So if your desire is that quantum field theory is not complicated enough, knock yourself out. Okay, so I want to start with a simple model. Here's a Lagrangian. What's the physics here? So I'm going to take a Dirac equation, and I'm going to take a scalar field, and I'm just going to couple them together so that the scalar field gives the Dirac equation, the Dirac particle, an extra mass. And that's all there is in this Lagrangian. This is some old stuff from the 80s. So what's the problem with simulating quantum field theory on a quantum computer? Well, suppose we want to work in a space of total, in a sector of total momentum. Well, I can have left-moving particles. I can have right-moving particles. So I can construct in 1 + 1D my fixed total momentum out of an arbitrary number of left movers and an arbitrary number of right movers. I guess I'm using your left and right. And so there's an infinite number of possible occupancy states, even at fixed momentum. And that means I have to cut off all those occupancies in some way, which means I can never simulate the true Hamiltonian. So the cutoff, of course, will introduce an error in the simulation. That means I need a large cutoff to make this error small. That means my problem is getting too big. So why does the light front help? Well, if you think of an observer, might as well make it Einstein, moving to the left at the speed of light. Did you know Einstein didn't learn to ride a bicycle until he went to Caltech in 1933? I just went to Caltech, but I knew how to ride a bicycle already. Every massive particle, according to this observer, is moving to the right. So in the light front, all the light front momentum of massive particles has the same sign. So that means that if I take fixed light front momentum, there is a finite number of ways of dividing that fixed light front momentum among the particles. So I can fix my total light front momentum and have a finite number of states, so no cutoff in 1 + 1D. And so I don't have cutoff-induced error cutoff-induced errors, I can just look at the piece of the theory that I'm interested in. Okay, so what we have here in this 1 + 1D theory are what we call momentum space orbitals. They're just, as they are in chemistry, they're single particle eigenstates of momentum. Except it's not the momentum you know and love, it's light front momentum and light front energy. And so here's this sort of Dirac type dispersion relation. And here we call these particles and antiparticles, and we have to have a Dirac C kind of argument. If we look in the light front, all it is you just turn your head through 45 degrees. Now the particles live over here, and the antiparticles live over here. And so we can do a quantization in this light front momentum, this light front picture, where we have single particle solutions, and here are the fields in terms of these creation and annihilation operators. Okay, so all this is just saying in equations what I just said in words. So here are the states. Here's my light front orbital called 1, which is a fermion with momentum 1. And M1 is the occupation number, but it's a fermion, so I can have 1 or 0 of those. Here's my orbital 2 with momentum 2, and I can have 0, 1 of those, up to some cutoff lambda. And these are the antifermions in the theory, and these are the bosons. So this total light front momentum also goes under the name of harmonic resolution, and we can figure out what does this mean. So it's not, it's a conserved quantity in the sense that the Hamiltonian splits up into blocks of fixed light front momentum. But if you go through the algebra and look in the center of mass frame, what you find is that the total light front momentum you're looking at, if you're quantizing in a box of size L, is the size of that box measured in the number of Compton wavelengths of the particle. So this K is which is called the harmonic resolution, is really a resolving power of the theory in that sector. So this is a sort of very nice realization of the idea of the Heisenberg microscope, I think, in this picture. So when I'm increasing K, I'm not changing the physics of what I'm doing, I'm changing the resolution at which that physics is appearing. Okay, so there's a Fock space representation for all these operators. And there's a novelty here, which is that the invariant mass operator, will tell you in the interacting theory what the particles are in the interacting theory, is independent of the size of the box you quantize in. So when you write down the Hamiltonian, it's considerably more complicated than chemistry, but it has 3 basic terms. Has a vertex term, meaning a fermion can bounce off a boson. Has a Siegel term, a fermion and a boson can come in, and a boson and a fermion can go out. And it has a fork. This is called a Siegel because it doesn't look like a Siegel. And this is called a fork because it does look like a fork. Okay, so what do we want to calculate? Well, in the case of chemistry, the target is relatively easy. You want to calculate the electronic energy of a molecule. That's important because that will tell you which molecules are stable. It'll tell you which reactants go to which products, at what rate. In field theory, the natural thing to calculate would be some kind of scattering cross-section. But that's a dynamical quantity. It doesn't look like anything we know how to calculate from our experience with chemistry. However, this is a picture of the interior of a proton. So there's this thing called the LHC that bangs protons into each other. And protons are big bags of mess, I've learned by this. But the mess is described statistically by something called the parton distribution function. Because when 2 protons hit each other, it's really 2 of the constituents that are interacting. And so if you want to calculate the cross-section, you have to know some statistical information about the probability of what kind of constituent is interacting with which other kind of constituent. And so if you look here, this is a measurement of the mass of the W particle. The total uncertainty here is 28. The contribution to this of our lack of knowledge about the interior structure of the proton is 24, or almost 24. So this is a good target for a quantum computer. It's a very hard problem that has a real impact on some physical measurement. I always think this is supposed to be this is from Fermilab, but it's supposed to be a graphic of a proton, but I always think this is what a particle physicist's brain would look like. It's just particles and particles and particles. Okay, so I'm almost out of time. Let me just cut to the chase here. So what do we do? How do we calculate this? So we map particles to qubits. We can do this using the very similar techniques that we used in chemistry. We can prepare a state, by which we mean that we take a state of the free theory in the field theory and we switch on the interactions and we develop some composite particle that has inside it different fermion and boson content. And then we can estimate one-body operators which will tell us this PDF. Okay, so we've got some time for questions. We can do this in the direct mapping, and we can also do it in the compact mapping, but I'm just going to skip these details. And the cost is basically cubic in this harmonic resolution. Now, it's difficult to compare this to lattice approaches, but we're trying to work out exactly how this compares to other approaches. Okay, so just to sum up, so chemistry is now, I think, pretty well established as an application of quantum computing. The front form is really a promising approach to simulating quantum field theories on a quantum computer. And the reason is because we've found you cannot have a approach to quantum field theory that has in it a fixed number of particles because of pair production. But the front form contains an operator that plays the same role that the number operator plays in chemistry. It's this fixed harmonic resolution. So the scaling is a power, the simulation cost is a small power of k. This is all in 1 plus 1D, and we're currently working in figuring things out in more than 1D. So I should thank you for your attention and thank the people who paid for this. And this is Michael and William, who are my current graduate students. And I should tell you, for any undergrads in the room, the application deadline for PhD programs at Tufts is the 15th of January. Please be in touch if you're interested. Thank you very much.
Just puzzled at how any physical problem in that particular front format can have a vanishing set of
So the vanishing COM only crops up when you're trying to interpret what the harmonic resolution means.
One of the downsides of front form is converting that back to.
Yeah, this is an excellent question. So. It turns out that you can calculate the PDF without doing that. So you can calculate it directly in the front form. But yeah, you do have this worry that your simulation box is just going to fly by whatever you're looking at. Well, yeah. Yep.
Maybe you mentioned this issue of question regarding the light cone. That the vacuum is unchanged. So some of the interesting field theories involve precisely non-trivial vacuum, symmetry breaking and all of that. So any idea on how that can be smart? Because the method is very nice.
No, we haven't thought about that, to be honest. So you mean that there are theories in which even the light cone vacuum.
Uh-huh. Symmetry breaking model.
Uh-huh.
All
Uh-huh.
Now, QCD itself is a non-trivial vacuum. Nevertheless, I think the reference wrote down by Gerlach et al. Did make some progress in
Yeah.
the last 10 years working in the light cone.
Yeah. Yeah, so I don't think, I guess we don't really see ourselves as contributing anything new to the light cone approach. We just want to take that and try and use it on a quantum machine. Yep.
If I could go back to quantum chemistry application.
Sure.
I know you phrase in terms of doing better computation, but can you go back afterwards and say, does it teach you physics? When you think about the fact that you can put things in terms of doing many operations in parallel, does it teach you anything about selectivity of the behavior?
Well, you know, when I got into this business, I definitely used to think of quantum computers as this all-powerful thing that you would just feed in the nuclear coordinates and it would vomit out the energy and that would be the end of the story. I think in reality, you know, quantum chemistry is a very well-developed subject and there are many problems they can solve perfectly well. So I think quantum computing would really contribute to our understanding more than it would just be a machine for churning out answers. And the way that would work is to take problems that are, sort of take the difficult problems that the known methods don't work on or don't agree on, and try and settle what actually happens in those cases. So there's a famous, or there used to be a famous, and the problem with finding those examples is that chemistry is always moving forward. So we used to invoke the chromium dimer. If you take nitrogen and chromium, they have horrible multiple bonds. So there's a lot of electron correlation that results in them being stable molecules. So, you know, methods that don't handle electron correlation properly won't bind them. And so if you could settle the, you know, if you could really settle the issue of what the correct answer is, you could then compare against the other approximate methods and figure out which one is getting the right answer.
What I was kind of hoping for, maybe it's a pipe dream, is that you know, there's some hidden conserved things that makes this a homework, undergraduate homework problem,
Uh-huh.
opposed to a multi-million-dollar industrial operation. I'm just not seeing it because I'm thinking in classical terms.
Well, sometimes I joke that when I'm optimistic, I think we're going to build a quantum computer and solve these problems. And when I'm pessimistic, I think we're going to have an insight like this and solve them with a pencil, and we won't need to build a quantum computer. But I think there's some evidence, or there's at least a body of work working in the opposite direction. And this is a kind of classification of Hamiltonians from the point of view of computational complexity. So there you can ask, how complicated does a Hamiltonian have to be before finding its ground state is the quantum equivalent of NP complete? So these are things that would be like the quantum analog of glassy problems. And certainly, you know, there are certainly versions of chemistry Hamiltonians that fall in that class. They just don't look like molecules. And so if we can continue making progress in that direction, there you can find the problems that are too hard. And so where that lands is, we don't know yet. So.
There are no more questions. Let's thank Peter again.
Thank you.